Okay, we are now digging further into this topic, and we're going to dig into fossil fuels. And one of the drivers, of course, is the great urbanization on the planet. 8 billion people, 4.4 now living in cities, projected to be 7 million people by 2050. And year 2000 was only 35%. So here's yet another hockey stick that we are seeing. And all of us who've traveled, I myself have worked in microfinance for a while, been in the slums of both urban slums of both Africa and India. We know what this urbanization means for the environment. So how can we mitigate and find solutions? Here to dig into this very complex topic of urbanization and planetary health is Francesca Costabile at the Institute of Atmospheric Sciences and Climate in Italy. Welcome up. Give her an applause.
Okay, urbanization is a topic which has attracted a lot of interest in our community. I don't know if you know, there is also a nature journal dealing with it, Nature Cities. And, you know, the first interesting paper about urban health dates back to more than 50 years ago, 1971. Urban health and environment, a new approach. And we are still there, I think, because we need a new transdisciplinary approach spanning from policies, legislation, to air pollution, food, plastic, noise, heat, and urban forestry. And now, you know, I worked for a lot of period in the most polluted cities of the world, in China. But now what I'm really interested is what is happening in the high-income country cities, where this is the study Jos I was talking to you about here. Now it looks, it doesn't work. Now it looks like this is a science paper. The immunological profile of the people living in urban areas as compared to rural areas is different. You know, this is a huge result, and this is where we are trying to focus our attention. And the benefit for living in urban areas in the high-income countries are now less than living in the countryside. I have to say that 2 years ago I moved, I left Rome, and now I live in the countryside. While in the low-income countries, people are still moving. I remember in China, the people going to cities were considered in a new life. In high-income countries, it's the opposite. There is now a paradox that the well-being, social satisfaction, and economic satisfaction of the people living in urban areas, in the high-income countries, is less than living in rural areas. And this is the first transition I want to talk about. The second one, and this is a nice paper, the first I found from the Global Burden of Disease Studies, describing this epidemiological transition. We have seen a lot of works dealing with mortality. Years of life lost is the variable from the Global Burden of Diseases. But what about the years of life lived with disability? Children start their life with autism, neurological problem, cancers, diabetes, and they will live all the life long with it. This is very common now in high-income countries. Years lived with disability. Morbidity is the new problem in the high-income countries, urban areas. Mortality, probably a lot of science has been done to decrease mortality. We know very well the exposure response curve for mortality, for everything, but not for morbidity. So the author here say, probably is now the time that research will go towards what debilitate rather than what kills. And this is where I work. I've started in the air pollution. I'm an aerosol scientist, basically. Air pollution is recognized as one of the leading factors for death in the world. This is a Health Effect Institute report, 2024. However, even here, we are in a transition because particulate matter air pollution has been recognized for mortality. I mean, there is strong evidence in this sense. However, for the development of diseases, for the progression toward diseases, we still don't know how to measure it, which is the right metric. PM2.5, the mass, the number, the surface. Most of you are health people, so working with you, I understood that oxidative stress may be an important hallmark for the progression of diseases. Oxidative stress-related inflammation, DNA damage are considered as an important point to consider the future development of diseases in people. And on the other side, particulate matter air pollution can induce or bring exogenous or endogenous reactive oxygen species. So this is where we started, to connect oxidative stress in humans, in cells, but also in plants, because also the vegetation reacts with oxidative stress responses. And with certain properties of the particulate matter, which can produce this oxidative stress, the particle-bound reactive oxygen species. What we do now, this is our approach, an exposome approach, where we expose this is not just me. We are a group of transdisciplinary toxicologists, epidemiologists, modelers. We cannot do it alone, obviously. Humans, because we work in the open atmosphere, so we don't need to expose the people to high concentration. Myself, I am in Rome, in the cities, I am exposed, and we take samples from us, like saliva samples, urine samples, blood samples, and we measure biomarker, oxidative stress-related biomarkers in people. Also in human cells, exposed directly to the air-liquid interface into the atmosphere without any collection, and also to plants. And we measure biomarkers of oxidative stress in this cohorts, I have to say. And what we do is this is where I have most of my knowledge, we characterize the exposure by looking at the atmosphere, not at single particles or heat or noise or whatever. We select a particular condition of the atmosphere. Here you see 3 different atmospheres that you can have in the urban areas. One is here characterized by larger particles, higher temperatures, sunny conditions, is the accumulation into the atmosphere that you can have, where most of the particles are big. The focus is on particles because this is where I have most of my knowledge. In this case, you have larger particle, PM2.5 mass concentration is the metric that is mostly used. These are big, I have a solid core, and these toxic molecules, the reactive oxygen species, are bound over the surface. And what we measure, what we observed, is that they start reacting over the surface of the particles. While on the opposite case, you have new particle formation, is after the rain, after strong ventilation, when the atmosphere is clean, and with this weather extremes, this is a very often condition in urban areas as well, but we don't have fossil fuels emission. So we have this new particle formation without any solid core, and in our experiments, we have not seen any toxicity in this case. The worst case scenarios is strong rainfall, strong ventilation, so after weather extremes, sun, and working days in urban areas. We have emissions, a clean atmosphere, but we have fossil fuels producing metallic nanoparticles with a core metallic, and a lot of reactive oxygen species and toxic molecules that will bound on these very small particles. And what happened is that these toxic molecules that you see here, and that are represented by this line here, the particle-bound ROS, can bound either on the larger particles, the one that were measured in the past as PM2.5 mass concentration, that you can see here by this black curve. This is the condensation thing. If there are larger particles, reactive oxygen species and toxic molecules will bound to the larger particles. You see, they start reacting, because the particle-bound ROS increase only when the PM2.5 mass decrease. While if you have the tiny particles, the Trojan particles I call them, because they can enter into the human body, they can bring these layers here of toxic molecules wherever. And they cross the lung barrier and they enter into the circulation. Only if we don't have these larger particles, the toxic molecules will go over the Trojan horse nanoparticles. And you can see here, this is the diameter of the particles, 20 nanometers particles. And this is how I can explain this complicated plot, where you see here, this is oxidative stress gene expression patterns in human cells, and oxidative stress related inflammation gene expression patterns in human cells. Above 1, we have an oxidative stress control, which is less than the treated cells. So above 1, we have oxidative stress. And these are the lines here. In this case, we have a PM2.5 mass concentration, which was the metric very well used for mortality, which is low. You have 7 micrograms per cubic meter. But you have particle bound drops, which is the red line, which are high, and nanoparticles below 20 nanometers, which are high. In this case, where you have above 50, 55 micrograms per cubic meter of PM2.5 mass concentration, so very large particles, a lot of mass, you don't have any oxidative stress. So as far as we consider diseases, not mortality, PM2.5 can even be inversely related to oxidative stress. And also, if we talk about interleukins, the protein, which have been studied for so much time by epidemiologists, and you find it here in the y-axis, while in the x-axis we have the mass of deposited particles over the cells. These are points that were done at the higher concentration, and so we have high interleukin. But we can have the same quantity of protein, of interleukin, so inflammation, at the very low concentration, provided that the color of these dots, which is fossil fuel aerosol fraction, is high. And this is the last result. I have more results, but they are still ongoing, so I cannot present it now. But this is the last results where we measured in the atmosphere the fraction of the atmosphere under these particular atmospheric conditions dominated by fossil fuels. And on the y-axis is the oxidative stress. And you see that the higher the fossil fuels aerosol fraction, the higher the oxidative stress. While these fossil fuel sources to the atmosphere are either aged, and this is the case after 24 hours, because this is the condition that you usually have if there is rain, there is strong ventilation, at 6 o'clock in the morning or during the night. So all of the PM2, the larger particles decrease. Then you have the rush hour at 7, 8 o'clock, and you have this increase in the emission. These nanoparticles from traffic forms increase, there is sun, reactive oxygen species increase, and you have these big responses that, please note, occurs after 5 minutes. We measure the responses, oxidative stress responses, after just 5 minutes of exposure. And what we are describing in this paper is that this oxidative stress biological responses will become, after 24 hours, an inflammation response with a wave of different cascade impacts into the human body. While if you have these sources mixed with biomass burning or other urban sources, you have no oxidative stress responses. So I was trained to provide solutions today. Solutions to me is to have something to measure, science, evidence, and we have to measure. So I spent my time looking for metrics that can be used to mitigate the sources or whatever. Now we are in a situation in Europe where we have a new directive, and the new directive is asking us not to measure PM2.5 alone, but to move towards this new pollutants, nanoparticles, oxidative potential, which is good. We still don't have threshold, but we are asked to measure. And also to consider the short-term effects. Not as short as 5 minutes, but at least 24 hours. And here I want to compare not mortality, but disease development as indicated, but please correct me if you don't agree, as oxidative stress and inflammation on the y-axis, with the mass concentration of PM2.5 or the total number of particles, UFP particles, the nanoparticles I was talking about. You see, under these conditions, you have no threshold. Usually, the mortality studies report exposure response curve where there is an increase in mass concentration and there is a linear increase in the mortality. For the development of disease, probably this is not the case, and you can also have an inverse relation. Now we are working on a global study because these are mechanistic studies where we work to understand the mechanism. We have applied the same approach to a global study that we are going to publish, I hope, very soon. And we have also found this inverse relationship with PM2.5 mass concentration. While if you look at nanoparticles, at least you have a threshold. Below this value, you have no oxidative stress. And also the spatial distribution of PM2.5 and UFP are different. If you look at, this is the Po Valley, one of the hotspots in Europe for pollution. Usually I'm told, the Po Valley is very polluted. It depends. If you consider PM2.5 and all the diseases, especially mortality related to PM2.5, probably all of the Po Valley is polluted. But if you look at UFP, the nanoparticles data, you see the cities. You see here. This is Bologna, this is Milan. Talking about urbanization, probably ultrafine particles are a very good metric for urban emissions. But I want to say that it's not just ultrafine particles, it's not just the dimension that really matters, because if you compare only the total number concentration here with the metallic nanoparticles here, these are the number concentration of 20 nanometer particles and insoluble copper particles, which I think now are the major concern in urban areas. The situation, this is a better metric to measure. So measure metallic nanoparticles may be a solution. Before the last slide to conclude, what I said before, we cannot just treat air pollution in isolation. We have to treat exposure with an exposome approach, but also the atmosphere with a kind of exposome approach. We expose both plants and people and cells all together, but this is a very nice increase in temperature, average increase in temperature of 0.5 degrees per year. So 2 degrees in 4 years in Rome is an average temperature, which is quite high. As a result, we have found that there is also a nice fossil fuel nanoparticle fraction increase because the people do not heat. So the atmosphere change, and we have more nanoparticles under this condition. The plants are more affected by this, and also the humans. And humans buy more vehicles. The increase in vehicles has been astonishing. 1 minute. Concluding, we are in a transition driven by our socio-demographic status, so we are not safe in the high-income countries. We live more, but we live, our children live with more disability, and we too. Young people with cancer. Urban health is a concern now, and probably I hope we have to measure, we have to find the right matrix. I hope that oxidative stress and inflammation, but this is open for discussion, are a good point for you. From our point of view, I think that now metallic fossil fuel related nanoparticles are what we have to measure. And for sure, fossil fuel, not just combustion, but in general, the fossil fuels in urban areas are the big threat. Thank you. I think I have 30 seconds left.
Thank you. We will dwell moving into if oxidative stress and inflammation are good biomarkers later on. The Lancet Commission on Pollutant and Health concluded that air pollution is probably the leading environmental cause of global disease and premature health. So we're not only talking about lungs and respiratory disease, there is cardiovascular, there is neuropsychiatric disease. So what happens when we inhale those ultrafine particles? Where do they come from, and how can we create lower emissions and higher protection? Forward. Jos?
Yeah.
With a last name, you have to pronounce it because it's like, I've been trying. Yeah. Jos Lelieveld.
That sounds great. Yeah.
It's Dutch. You are most welcome, and you are from the Max Planck Institute of Chemistry in Germany.
Yes,
Welcome.
yes. Yeah, my my research focus is on atmospheric chemistry, but I noticed that people writing on this topic were always motivating their work because it's bad for health, air pollution, and it's bad for climate. And a lot of people were working actually on the link with climate. I think we will hear more about this later. But in my field, not too many people were connecting to the health community. So I thought this was important to do. And what you see is the city of Tokyo on a clear day and on a polluted day. And on the left, you see this brownish haze. And actually, when you look at air pollution, you can actually see it. Of course, you've seen it all yourself. But what you see are particles. And the yellowish color is NO2, but most actually of what you see are particles absorbing and scattering sunlight. And that property of these particles is also quite useful because that's why we can see them from space. We have different types. Actually, it's like a soup of, we just heard that, you know, very small particles, we call them ultrafines, and we have bigger ones, we call fine particulate matter, and then we have the even bigger ones. I mean, they are 10 microns, they're not really big, but we call them coarse particles. And they deposit in different parts of your respiratory system, and some of them actually can go beyond. So we define them in terms of what we call the aerodynamic diameter of these particles. The larger ones we call PM10. They deposit in the upper part of your airways when you inhale them. They have typically a large component of natural sources. The smaller ones that also Francesca talked about, the fine particulate matter, PM2.5, is smaller than 2.5 microns. They can actually reach deep into your lungs, and they have high concentrations of pollutants, actually. And the very small ones, which I will also be addressing today, we call them ultrafine particles. They're smaller than about 100 nanometers. And they can actually transmigrate from the lungs into circulation, and this has been shown, I've been involved in these studies, cause oxidative stress and inflammation in organs and arteries. So this is what you see here to the right. So let me put these particles a little bit in perspective, because they have properties that are also quite important to health. If you look at a cubic centimeter of polluted air, you may find, I mean, this is scaled obviously, you may find a few PM10 particles. They're not very abundant. And then you have maybe a few hundred of these 2.5 micrometer particles. But actually you have like 10,000 or more. Like in a polluted city like Milan, as we've just seen, you find like 20,000 or even more particles per cubic centimeter. And even though these particles are really very small, you can see that, but the A over V is this is the surface area over their volume is 60. And if you compare this with here, the bigger ones, they have a surface to volume area which is much lower. Plus the fact that the very small ones are enormously numerous. So actually the surface area that gets into contact with the tissue in your body is dominated by the very small ones. We distinguish short-term and long-term impacts. We heard this morning about asthma also. So when you have high concentrations that you're exposed to, especially vulnerable people, coughing, difficulty breathing, asthma attacks, and other, can it even get even much worse actually, hospitalization if the air pollution is very bad. But what we have looked more into is health outcomes and impacts of long-term exposure. So you can say chronic exposure causes chronic diseases. And as you said, not only respiratory disease, but also cardiovascular disease, neurological. And this is what you see here. Oxidative stress, pulmonary, systemic inflammation, vascular dysfunction, atherogenesis, impaired metabolism is what you find as the impacts. There are health outcomes for which there is very strong, mostly epidemiological evidence. But of course, there is also mechanistic research on this in clinical studies. Is ischemic heart disease causing heart attacks, stroke, respiratory tract infections, also in children, a lot chronic obstructive pulmonary disease, asthma, lung cancer, and diabetes. Now, diabetes is really an indication that there's something happening at cellular level. And there is really growing evidence also that decreased birth weight, so children are affected, premature birth, arterial hypertension, and also neurodegenerative diseases, so like dementia and even Alzheimer. Now, this is from the latest Global Burden of Disease report in the Lancet of last year. And here we see that the number one risk here for disability-adjusted life years loss is particulate matter pollution. So we have 8% of DALYs are being attributed to particulate matter air pollution, which is at the same level as high blood pressure. I mean, high blood pressure is the number one killer, as most of you know. In terms of mortality, it's the other way around. So it's high blood pressure, number one, and particulate matter air pollution, number two. But these are the main risk factors for disease worldwide. And I'm going to explain why these things are going up so high, because actually in previous reports, the air pollution was ranking lower. Now you can see some of the other risk factors, obviously. The good thing about the PM2.5 particles is that you can see them from space, from satellites. They scatter light, and there are many instruments measuring for decades now these particles from space. So we have very good data sets. We now have data sets on this at 1 kilometer resolution. This is the highest resolution of long-term exposure, basically. Of course, you see in dusty places like the Sahara and also the Arabian Peninsula, there is high PM2.5. This is PM2.5. There's also high PM10, but there's not many people living there. So if we look at it in terms of exposure, we see global population-weighted exposure is what we can calculate is about 32 micrograms per cubic meter. And the WHO guideline concentration is now 5. It used to be 10. It has been revised a few years ago, so it's 5. So we're more than 6 times higher than the guideline concentration recommended by WHO, which also means that more than about 99% of the population is exposed to levels that exceed the guideline concentration. Now, let me try to explain you how we get to these numbers. These are high numbers, and also why the numbers are changing. So an important parameter that we need is, this is my field, we look at exposure, so global exposure. But then we need to compare that, or we need to combine that with hazard ratios for different disease categories and also for all-cause mortality. Another reason Francesca mentioned that we need to study more morbidity. This is absolutely correct. But the best data that we have, and this is why we do these studies, is on mortality, especially at the global scale. Now, the dashed lines here are curves that have been used also by the Global Burden of Disease, Murray et al., and you can see them here. These are the hazard ratios. These are the concentrations. And what you see here, for example, for diabetes type 2, is that this curve is almost flat. The reason being is that in the past, the epidemiological studies that were needed to design in order to derive these curves were insufficient in terms of exposure to high concentrations. So what was done is use proxies like secondhand or smoking studies, epidemiological studies. And actually that distorted the picture. So we get, basically this curve means that if you go from 100 to like 30 or 40 micrograms, there's no improvement actually in air quality, which is of course incorrect. So we now have better data. We have several dozens of studies, epidemiological studies, including in high concentration countries like China and India. And now we have these solid curves here. And here you see diabetes is much higher now here. And also it is not as nonlinear as these curves. And you see CV is a cerebrovascular disease leading to strokes, ischemic heart disease. There are quite big differences. So using these proxies has actually led to an underestimation of these hazard ratios. Yeah, oh, oops, now I have to go back. Yeah, I was using it, but I'm guessing that. Yeah, okay. Yeah, please go on. Thank you very much. So we're now putting these things together. So the hazard ratio is actually used as an approximation of the relative risk. And the relative risk can be used to derive the attributable fraction. And then we have all the information from the global burden of disease on diseases, and we put exposure and these hazard ratios together, and we get these numbers. And the total that we find is a little bit more than 8 million per year, excess mortality, which is very close to what the global burden of disease has been published last year, 8.1 for particulate air pollution only. We have about 400,000 attributed to ozone pollution, which is also a big number. But actually, it's only 5% of this total number. 400,000 is like a few times the number of people that die from malaria. And the global mean loss of life expectancy is more than 2 years. And you can also see where this is being concentrated. It's concentrated in areas with high pollution levels, but it's also concentrated in areas with high density in population, and especially where this comes together. Okay. Seem to be having difficulties moving from one to the other. Okay, now we go to the attribution. And here, my field, modeling air pollution at the global scale. So we model the sources, the atmospheric processes, and then we have the exposure. And then we can, of course, play with these models and say, okay, what would happen if we would not have fossil fuels, for example? So there are a number of things that run on fossil fuels, like energy production, traffic, a lot of industry. So if you take that out, you can see that there is a huge difference here. And this is the mortality rate, actually. So it's also an important distinction here. What I have shown before was the total mortality, and the mortality rate, of course, is normalized to the population. And still here, you see countries like India and China scoring high, but you also see that Eastern Europe, for example, is scoring very high. And if you take out the fossil fuels, you'll still have, especially in countries where non-fossil fuels and also natural sources like desert dust are important, but it's a huge reduction. So in terms of what we call avoidable mortality, avoidable being the anthropogenic fraction that can be controlled. So desert dust cannot be controlled. Wildfires can, to some degree, but we assume not be controlled, even though they are to some degree anthropogenic. So this is not involved in avoidable. 80% of the avoidable mortality related to air pollution is related to fossil fuel use. Okay. We can also attribute them to disease categories, and I'm going to do this quickly because my time is running out. And the point I really want to make here is the countries, or the pie charts that you see on top are on high-income countries, and the ones that you see at the bottom are in low-income countries. And you see that the brownish fraction of these pie charts in low-income countries is much higher. And this has to do with child mortality. And so we have all the disease, we can do this basically for every country. And, but the point here is that even though the total numbers of premature mortality or excess mortality in these countries may not always be so high, actually in Central Africa they are high, but there is also a high loss of life expectancy because of the children's mortality contribution. So what we can then do is look at the loss of life expectancy related to different causes, and this has helped me very much to put this into perspective. So if we look at comparing ambient air pollution, this is a somewhat older study, 2020, tobacco smoking was still at 2.2 years of life lost. And you see parasitic vector-borne diseases are very high, of course. This is mostly malaria in sub-Saharan Africa, and HIV, AIDS, the same. But if you look at global loss of life expectancy, you see that air pollution is really high on top of these. And you can also see that Africa is, involved in many health-related problems. Okay, then I would like to, following Francesca, also talk a little bit about ultrafine particles. As I mentioned, their surface area is large. They can transmigrate into circulation and reach organs. And if you want to know more about this, I was involved in some research showing that actually the responses of the larger ones are in the lungs and the smaller ones are in the organs, in the remote organs. By the way, it's okay to photograph this, but this is unpublished work, so I would like to ask you not to distribute. And here we have the problem is that we don't have the measurements from space. The small particles you cannot measure from space. You have to have ground-based measurements. So we've been collecting these measurements and using AI techniques, which are fantastic. You can not only put a lot of data together, but you also have advanced methods to characterize uncertainty. And you can also derive information about the sources. So this is what we have done here. I'm going to move forward on this one. So, and then we can compare, we have to, when you do these machine learning techniques, you have to sort of take out data for testing. So you have the original data, etc. And we come to quite high correlation coefficients of R squared more than 0.9 and relative errors that are quite small, like around 30%. They're bigger, by the way, in the rural environment, but that's not so health relevant because, as again Francesca has shown, most of these particles are relevant for cities. And I don't know why I'm having these problems. Okay, now I think I went too quickly. Could you help me up there?
Ska tillbaka en slide.
I need to go one back. Now one forward. And I know why this is difficult because this is a very heavy, like 20 megabytes or so image.
Det ska ligga en slide mellan de här två.
And it's even downsized from the original resolution. And now we can resolve cities, like, all of these. And actually you can see the global chart seems to be relatively low, but if you zoom into cities, you see, and this is long-term average, so this is not some specific, this is long-term concentrations. We have now data between 2000 and 2020 of up to like 40,000 particles per cubic centimeter that the people are exposed to on a long-term basis. And then, of course, we can do the same tricks. Yes, thank you very much. We don't have so many cohort studies available to do the same as we could do for PM2.5, but there are really quite a number of very large ones, with 4 very large ones. And we've used them here, and we see that, basically 90% of the ultrafine particle-related mortality is in urban environments and most in urban centers. Also, and this is, I think, a conservative estimate, we find that about 2 million excess deaths per year can be attributed to the exposure to these ultrafine particles. So that would be about 25% of the PM2.5. But it is a conservative estimate. And if we look now at the mortality rates normalized to population, then we see a different picture. We see India is now lower than China, and we see high numbers in Korea, in Taiwan, and in Singapore is one of the bad ones, and also in parts of Europe. And even America and Canada are sticking out here. So for the ultrafine particles, we have a different exposure pattern. We can also link them to sources. So this, again, we do with models. there's, I guess, not much time to go into this in any detail, but we can maybe compare two. One here is sub-Saharan Africa. You see, domestic energy use, burning of woods and other stuff is important. And if you look at, for example, high-income countries, we see that industry, energy, and traffic is important, but it's actually not the only one, and domestic energy use is a smaller one. So to summarize this, the global estimate of excess mortality related to PM2.5 and ozone, again emphasizing that PM2.5 is 95%, is around 8 million per year. 5 million is related to fossil fuel use. This is about 60% of the total, but it's 80% of the avoidable air pollution. And then we have a loss of life expectancy of about 2.2 years and about 2 million per year related to ultrafine particles. And the obvious and conclusion is that phasing out fossil fuels is a highly effective intervention to improve health, save lives, and is part of the United Nations goal of climate neutrality. Thank you very much.
Thank you. Clapping is great for the brain, and also rising up is great for testosterone, mobilizing the big leg and butt muscles. So it's good for you guys too, and it's good for the speakers. Okay. Thank you very much, Jos, for illuminating. Ray Pierrehumbert, correct pronunciation. Where does the last name come from?
Oh, it's from the Franche-Comté. So it's actually predates France.
Predates France.
But I'm a Jersey boy. So
okay. Well, for science to contribute to planetary health choices, we need to measure correctly, but also be able to weigh one risk versus another. And Ray is here from Oxford University to question how we judge the relative impact of two greenhouse gases, carbon dioxide versus methane. Welcome.
Yes, thank you very much. It's always nice to be back in Stockholm. So if you want to have a good treatment, you have to have a good diagnosis. The good diagnosis means having good diagnostics. And so the same goes if we're trying to fix planetary health or treat planetary health. We have by changing the emissions of different greenhouse gases. It really is essential to have an accurate measure of which greenhouse gases are responsible for most of the problem, or the extent to which various greenhouse gases are responsible. And so I put in methane as my prime example because it's the one that is in the news the most, and the soundbite I've been fighting against over and over again with many reporters, and it's like playing whack-a-mole, is that methane is 80 times worse than carbon dioxide. You could substitute in your other favorite short-lived greenhouse gases, and for this audience, I put in some of the things I've been doing on anesthetic gases recently, which I've started working on with an NHS anesthetist. But this business of, this is what puts the E in CO2e. This is the hidden thing that a lot of people don't think about when they see those figures about CO2e, equivalent CO2. And if we don't do this calculation of CO2e correctly, then things like policy implications or things like the INDCs that countries have committed to in their climate goals can give us adverse or wrong climate impacts. So working with the wrong kinds of metrics or diagnostics of methane or desflurane or whatever is like working with a miscalibrated blood pressure meter. And we can do better than that. I'm going to explain some of the issues there. For the most part, these metrics that are being used to make methane into, say, CO2e and other gases into CO2e, equivalent CO2, tend to exaggerate the climate impact. It's not to say it's unimportant, but they measure it incorrectly. But there are cases in which the standard metrics, global warming potentials, actually underestimate the impacts. But I'll show you how we can, what happens if you do this correctly. So to first give an indication of which kinds of gases we're talking about and what their lifetimes are. When I say short-lived gases, I mean things that are sort of decadal to 20 years or less. So methane has a 12-year lifetime in the atmosphere, mostly because it gets oxidized. But the issues are the same. The issues are pretty much the same for other greenhouse gases with decadal lifetimes, like hydrofluorocarbons, which are CFC replacements, tend to have decadal lifetimes. But then there's a big push, actually, in hospital operation sustainability to phase out certain anesthetic gases like desflurane, and maybe even phase out all anesthetic gases in favor of IV-based anesthesia, which can have very bad consequences for patient outcomes, I'm told. I won't say much about N2O because that's a kind of a complicated gray area. So first, let's talk, I want to tell you about the two different numbers that characterize a greenhouse gas. So first, I want to say a little bit about basic climate physics. Radiative forcing is a fundamental concept. So you get a certain amount of energy in from the sun, and that has to be balanced by radiation of infrared to space. That's been known since Fourier's paper in 1827. When you add a greenhouse gas to the atmosphere, carbon dioxide, methane, whatever, the rate at which you lose heat radiation, infrared to space, goes down. In order to balance the budget again, the climate has to warm up a certain amount. But the amount it has to warm up depends on how much that greenhouse gas has reduced the radiation to space. It's like adding planetary insulation, like putting on a sweater. It doesn't generate heat, but it changes the rate at which you lose heat. And now the reduction in infrared energy loss, this is a critical climate number, by a given increase in greenhouse gas is called radiative forcing, and more radiative forcing gives you more warming. We measure to characterize the potency of greenhouse gases at giving you radiative forcing. We use this quantity called the radiative efficiency, and so that's the rate. That's basically the number of watts per square meter of radiative forcing you get from an increase in atmospheric concentration by 1 part per billion. That's the standard. That's the standard unit that we use, watts per square meter per part per billion in the atmosphere. And to give you a feeling, 1 watt per square meter of total radiative forcing corresponds to about 3/4 of a degree of warming under sort of mid-range climate sensitivity. The radiative efficiency tends to decrease as the baseline concentration of a greenhouse gas increases. For example, CO2 has a kind of logarithmic dependence, radiative forcing of CO2 has a more or less logarithmic dependence on concentration. That's because when you have very little of a greenhouse gas in the atmosphere, you haven't used up the parts of the infrared spectrum where that gas is good at absorbing, and you gradually saturate it. And so this is a universal property. Low concentration gases have higher radiative efficiency. So as an example, if you take hydrofluorocarbons, which have roughly a decadal lifetime, they're present in the atmosphere at tens of parts per trillion. They have a radiative efficiency of 0.15 watts per square meter per part per billion increase. So if you increase the atmospheric concentration of an HFC by 1 part per billion, but notice they're only present in parts per trillion. But if you were to increase an HFC concentration by 1 part per billion, you would have a radiative forcing of 0.15 watts per square meter, compared to, say, the 4 watts per square meter you get from doubling CO2, which we're well on our way to doing. The anesthetic gases are present in the atmosphere at levels of well under 1 part per trillion right now. And they have quite high they do have high radiative efficiencies. Desflurane 0.47, which is partly because of its very low concentration, but also because of the structure of the molecule, which gives it a lot of absorption bands. Methane is present at a few parts per million right now, as opposed to CO2, which is present at over 400 parts per million. It has a radiative efficiency of 4 times 10 to the minus 4. And CO2, which is at a high concentration of something over 400 parts per million, it is has a radiative efficiency that's lower than methane, 1.37 times 10 to the minus 5. So this is straightforward physics. There's no difficulty in this is certain. This is well understood. So it's certainly true that per molecule or per kilogram in the atmosphere, desflurane will give you more radiative forcing in the atmosphere, more warming than that same amount, that same kilogram of CO2. But that's not the only part of the story. The other part of the story is atmospheric lifetime. And so greenhouse gases are characterized also by a lifetime, which is the time constant tau for the exponential decay of the atmospheric concentration of the gas once you release some of it. And most of the gases that I've indicated can be characterized by a single decay constant. They really do decay exponentially. CO2 is different because it decays from multiple processes over multiple timescales. But if you do need to, if you're forced to give it sort of a round number lifetime, it's around 1,000. It's 1,000 years is the right thing to think of. I'll show you results with an actual carbon cycle model that takes into account the multiple timescales of decay of CO2. But CO2 is way longer lived than any of these other gases. So here's a figure from a paper I was involved in. Some years ago. A whole raft of authors, and this is based on an actual climate, fairly comprehensive climate model, and a fairly comprehensive carbon cycle model. So I'm a geologist. I take the long view. Well, I'm a physicist, so I take a billion-year view usually. But this is a short time period by my standards. But this is going from the last ice age, 20,000 years ago, to 10,000 years in the future. Okay, and these different curves correspond in all of these case scenarios. We emit carbon dioxide at a certain rate for about 200 years, and then we stop. The different curves here correspond to the climate future that you get if you stop emitting at a cumulative carbon, a net carbon emission of these different amounts, like going up to about 5,000 gigatons. And here is the optimistic case that corresponds to roughly 2 degrees, 1,000 gigatons. But so the important thing is that once you actually stop emitting, the temperature stays fairly flat out to 10,000 AD. So in that sense, CO2 is forever. CO2 accumulates in the atmosphere. A certain amount of it disappears into the ocean quickly, but the rest of it is there from a societal timescale essentially forever. And this, by the way, is one of the reasons that ideas like sunshades or solar radiation management that rely on things that have to be renewed practically yearly are silly, are just a broken way of thinking about solving the climate problem or even insurance against what's happening in the future. If you rely on something like a sunshade to fight global warming, to keep the Earth habitable, you're committing humanity to doing that for the next 10,000 years. When have we ever done anything except reproduce ourselves for 10,000 years without fail? So this is important. So CO2 is forever, but methane is not forever. And so this is the essential problem in trying to find an equivalent CO2. There is no really right way to do it because greenhouse gases are characterized on a two-dimensional continuum. By the way, is there a time?
Yeah, you have six more minutes.
6 minutes, good. Okay, I'm doing okay. So so CO2, so greenhouse gases are characterized in this two-dimensional plane. There's the radiative efficiency here, and methane is up here, and desflurane would be up through the ceiling somewhere. And then there's the lifetime. CO2 is out here, low radiative efficiency, but it lasts essentially forever. And so to give you an idea of the different climate consequences, this is a simplified version, actually it's a pretty accurate version of methane and a simplified version of CO2. The blue curve, so in both of these cases, I have an emission of the greenhouse gas at a steady rate. I turn it on at year 0, and I have an emission at a steady rate out to 200 years, and then we stop. We go cold turkey. And so this solid blue line is CO2, and you can see the CO2 accumulates over that time. And then once you stop, the warming persists, and it actually persists out to 10,000 years if you do the CO2 removal correctly. So this is the same thing for methane. The warming goes up fairly quickly, but then because of the short lifetime, you come into the concentration in the atmosphere stops increasing. And so the concentration of methane stays fixed, unlike CO2, whose concentration keeps increasing no matter as long as you're still emitting some of it. But there is this slight additional increase because it takes time for the ocean to warm up. That's the stock version of that. And when you stop, you get a rapid decline in temperature, and then this long tail is from the ocean heat storage. Some people say that this is an advantage of controlling methane because you get instant gratification, as it were. I say this makes methane less urgent than CO2 because if you delay the reduction in CO2 emissions, you've permanently and irreversibly ratcheted up the temperature. Whereas if you delay the controlling CO2, you can still reverse it later. Okay, and what this means is that the right equivalence between a short-lived gas and a long-lived gas is not between a number of kilograms of the short-lived gas and a number of kilograms of CO2. It's between that doesn't even have the right units for conversion. It's between the rate of emission of the short-lived gas and a fixed number of tons of CO2. And so that means that a permanent reduction in the rate of emission of methane, which is an infinite amount of methane released, is equivalent to, in this case, about 50, is equivalent to this fixed little wedge of CO2. And so these metrics like GWP20 are broken in an unfixable way because they have the wrong units. They're kilogram per kilogram equivalents, whereas it really should be a kilogram per rate equivalent. So I was going to skip through that. And it can't be fixed. It's the wrong units. And to give you, and further, these global warming potential metrics, GWP20, 100, they fail to recognize that CO2 continues to accumulate in the atmosphere as long as emissions continue, but short-lived gases don't. So it leads to silly ideas like cumulative GWP equivalent. It just gives you the wrong notion. And so when they say methane is 80 times worse than carbon dioxide, what it really turns into in terms of what you don't see from that is this. Now my time base got cut off, but this is 1,000 years, so this is 200 years here. And so this is the GWP20 equivalent of turning on some methane emission versus the equivalent GWP20 equivalent of CO2. And so you see it does track, the two things do track in this first little bit of time, but if you were allowed to trade methane versus CO2 based on GWP20, or if you had your INDCs written on that, and this also goes for things like desflurane, the CO2 that you are allowed to emit by trading for that CO2 that CH4 reduction would give you this very large surface temperature change out into the future. Now we have a better way of doing it, but I don't have time to talk about that. So I just want to. I think I'll skip the methane flaring example, which is, again, if you allow an oil company to flare methane and take credits based on GWP20, you wind up with a way warmer, and emit CO2 in exchange, you wind up with a way, way warmer climate. But I want to just end with the desflurane example. There's been, push to ban desflurane. And since it has a GWP20 of 7,000, it looks like the world desflurane use is equivalent to taking 1.5 million cars of emissions. That's not actually a big number, but even that exaggerates the desflurane warming. I've calculated it, and so the actual warming from a sustained emission at the current rate of desflurane tops out at 0.00016 Celsius. And so compared to the benefits to patients to have the option to use desflurane or isoflurane, this is really not what hospitals mainly should be worried about. The other main implication is the climate impact of dietary choice, which has come out here a lot. And methane comes into that because methane is one of the primary ways that agriculture, especially livestock agriculture, affects the climate. And this is not a simple story, but again, using GWP 100 or GWP 20 exaggerates the methane component of that impact. And in our work early on, we've found that actually deforestation is by far the biggest climate impact of most livestock. But also, this is my last statement here, if you take GWP 20 seriously, then net zero, which Britain has committed to, would mean net zero livestock. But the answer is not that. The answer is something, but it's not that. And we do have this article in Bulletin of Atomic Sciences which tries to tease out just exactly what methane emissions really mean in terms of the net zero commitment. Thank you.
Thank you very much. Thank you. The importance of scientists who actually know their numbers. Very interesting. So we're going to dig into aerosols. Small particles generated naturally, of course, but also by fossil fuels affecting climate change. And Kevin Noone is with us, Professor of Chemical Meteorology from Stockholm University. Welcome.
Thank you very much. My clicker. This used to be me. I've got the stuff on the green on the right-hand side to sort of say that I work a lot with the economics community and training communities. And damn, do we need this conversation that we're having in this room with our economics colleagues. Really. But we'll park that and come back to it later. What I'd like to do today is speak with you about these four things. So tell you a little bit, I've been asked to talk about aerosols, clouds, and climate and how those things fit together. But then I really want to transition into connecting the dots and solutions, because that's why we're all here today, and talk about handling trade-offs, because aerosols, clouds, climate, health, and agriculture are intertwined. And there will be very, very difficult trade-offs that we need to deal with. How do we do that? In a lot of the trainings that I do with corporate executives and military people and even religious groups and whatnot, we talk about wicked problems a lot. We've been talking about wicked problems for the last couple of days. I'll exemplify that a little bit and then try to be a little bit positive. We don't have time for pessimism. I mean, what we've been hearing, particularly yesterday with Johan and others, like, dang, I just want to go home and crawl under a rock. We don't have time for that pessimism. So, back when I was a graduate student, way back in the early Pleistocene, I had the opportunity to work with Dave Covert. He was one of my mentors. And Dave's the guy on the left there. This is an AI-generated image, by the way. Dave's the guy on the left, and he had the opportunity to give a tour for Gary Larson, who is the cartoonist in back of the Far Side cartoons. And if you're not familiar with the Far Side cartoons, you should be. They're just genius, okay? So Dave was just excited. He's given the tour to Gary Larson, and he's showing Gary all these instruments that we use to count particles and measure how big they are and measure how much light they absorb and they scatter, and measure their chemical composition, and they bubble and they blink and stuff. And at the very end of this tour, Dave told me that Gary said, wow, Dave, thanks so much for that tour, but have you ever actually seen an aerosol particle? And of course, Dave had his Homer Simpson moment, like, don't. But you do see aerosol particles. And the view can be awfully dramatic times. So what you're seeing here is the west coast of Africa, Mauritania at the top. You got Senegal and the Gambia and Guinea-Bissau towards the bottom. And what you're seeing is Anna was telling us about mud, dried up mud that ended up being lofted into the air and causing problems for people's breathing. This is essentially dried up mud. It's not the big Saharan desert dust particles that are blowing off here. It's from intermittent stream beds and lake beds and stuff. It's red mud, actually. It's pretty dramatic, isn't it? Okay, there's a lot of aerosol particles here. But in terms of what aerosols or how aerosols interact with climate, I find an image like this, which is a EUMETSAT geostationary image, to be perhaps the best illustration of what the interactions are between particles and climate. And so what you're seeing here, well, I got to make an aside as well, because look at this image. This is just astoundingly beautiful. Our planet is tremendously beautiful. Why are we treating our planet so badly when it's this beautiful? I can't get my head around that so much. But that's kind of an aside, right? So let's get back to aerosols and particles. In the middle, you can see this sort of grayish, brownish blob, and you can also see sort of a gray, hey, look at that. A grayish, hazy thing going this way, right? That's going to be these dust particles coming from the African continent. Those are dry. We had the opportunity way back when to fly through one of these plumes in a project I was involved in. And you looked outside the window of the research aircraft, and it was white. It looked like you were in a cloud. It was a whole lot of scattering going on. But our instruments were saying there's no liquid water here. So it was just dry aerosol particles that we're seeing. You're seeing them because the photons coming from the sun aren't hitting the surface of the Earth. They're actually being scattered by those aerosol particles, heading back to space, cooling the planet, essentially. So it looks hazy, it looks white, because those photons aren't hitting the surface and heating it up. They're actually heading back to space. So that's one way that aerosol particles interact with climate. They can cool the surface because they scatter incoming radiation back to space. Some of them absorb that incoming radiation, and they can heat the atmosphere, but aloft rather than at the surface. Right? But the thing I've spent a lot of my nerdy time with is trying to figure out the interactions between those particles, the grayish stuff, and the really white stuff that you see. All that white stuff are different kinds of clouds. Down here in the southern hemisphere, you can see these are higher clouds towards the top of the atmosphere, cirrus clouds, we'll call them. You can see towards in the northern hemisphere, the lower stuff would be stratus or stratocumulus clouds. All the really bright ones are higher up in the atmosphere. Now, those clouds are made of droplets or ice crystals. And each one of those droplets or ice crystals started its life as an aerosol particle. So our planet would look very, very different if we didn't have these particles in the atmosphere. So that's the climate bit. Well, one more thing about the climate bit. One of the things that the aerosols can do to those clouds is they can change whether or not those clouds might precipitate. That's kind of important to us. They can also change larger scale circulations, like monsoon circulations. It's kind of important to us too. So aerosols have very important climatic impacts. But one of the impacts that you've seen several times, and Jos told us a lot about, and Francesca told us about as well, is that here you've got an image taken from the Griffith Observatory, which is kind of in the Hollywood Hills up above Los Angeles, looking towards downtown Los Angeles. And you got this lass at the bottom here skipping rope, presumably to become healthier, right? But she's breathing more deeply as she's skipping rope. And look at what she's breathing, okay? This is a decent day in Los Angeles, if you haven't been there. So there's kind of a paradox here that we need to deal with. Aerosols, as you've seen several times, are one of the planetary boundaries, and it took 3 attempts, but finally, a couple of years back, aerosols were, a boundary level was established for aerosols, and it's expressed as the difference in level, concentration level between the northern and the southern hemisphere. And it's expressed that way because that has an impact on large-scale circulations like monsoons and whatnot. But what I wanted to do mostly with my time is talk about feedbacks, talk about connections, connecting the dots. And I just want to talk about a few of those connections that have to do with aerosol particles. So the red thing there is aerosols. I've already told you that you couldn't have clouds unless you had those aerosol particles. So there's a connection between aerosols and clouds. We've heard a lot about the connections between this particulate matter and human health. Okay, so there's a direct connection there. But let's look at some of the indirect connections, right? So aerosols connect with clouds, but clouds are involved in monsoon circulations. Clouds give us precipitation. So there's direct links there, but precipitation and monsoon circulations impact on food systems and agricultural systems, right? So those food systems then feed back on aerosol particles. And here's one of the interesting things. So handling trade-offs. We've seen that if you increase air quality by cutting down the concentration or the emission of aerosol particles, that's a good thing, right? Between 5 and 10 million people die prematurely every year because of particulate pollution. That can be done. We can do something about that. But if we clean up the air, if we reduce that cooling effect that aerosols have on the climate, then global warming will accelerate even more rapidly. So this is another AI-generated image. This fellow's out trying to find his Eat Lancet breakfast bagel in Los Angeles. Okay, and he's happy in one sense because look in the background, you can actually see the San Gabriel Mountains from central Los Angeles in this particular case. You can't do that these days in Los Angeles, not very often anyway. So that makes him happy, but because the air quality and that cooling effect has been removed and Los Angeles heated up faster, sea level rise rose faster, and he's got to wade through salt water to find his breakfast bagel. Okay, now these are the kinds of trade-offs that we need to handle. And somebody earlier today said we just need, one of the things that we need to do is be honest about these. There are scientific bases for all of these sorts of issues. We need to be honest about what they are, such that we can have an informed discussion about what those trade-offs are, on what basis we decide to deal with those trade-offs. What moral basis, what ethical basis, what distributional basis we need to try to figure out those trade-offs. Talking about aerosols in food systems, like Jos said, you go ahead and photograph this if you want, but please don't distribute it because it's in review. But Sophie Tversky and other people, about 2 football teams of authors, have submitted the aerosol in food systems planetary boundaries analysis. So what the bunch is looking at is okay, so if we look at what food systems, how food systems affect planetary boundaries, what are those? You've seen this, or a different kind of version of this a couple of times already, but here's the interesting thing, at least for me. If we concentrate on the aerosol boundary, trying to remain within the aerosol boundary means different policies if you happen to be in the northern hemisphere or if you happen to be in the southern hemisphere. In the northern hemisphere, great. In the northern hemisphere, I think it was one of the polls was mentioning that, okay, so particle levels are going down in many places in the northern hemisphere because of changes, or cleaning up our energy-related emissions. So a lot of the material, the chemistry of the existing particles is oxides of sulfate or sulfur oxides of nitrogen and things like that. That's going down. We've been successful in that regard. Agriculture and agricultural emissions that lead to aerosol particles, the agricultural fraction of that is actually going up. And it's going up in the northern hemisphere because of ammonia emissions from agricultural productions. So in the northern hemisphere, to move away from that aerosol planetary boundary, we want to be limiting ammonia emissions from primarily agricultural activities. In the southern hemisphere, it's different because there, most of the aerosol emissions that are related to land use or land use change and agriculture are from biomass burning. So there we want to do something different. Okay. Now, aerosols is a wicked problem. This spaghetti bolognese plot is one of my favorite images ever. It comes from the World Economic Forum. I don't know if you guys read the World Economic Forum risk reports. I do, faithfully. They're really good. I love it because it's illustrative, for me anyway, of what a wicked problem is. So what you've got for these wicked problems, if you just look at this image, is, let's say, the big one there, climate action failure, right? That particular risk is associated directly to involuntary migration. It's associated directly to water crises. And the different colors are different kinds of risks. You've got environmental risks, geopolitical risks, economic risks, technological risks. So what you're seeing here is that all of these risks are interconnected. Now, most of us have been trained to make priority lists, right? You look and you say, okay, so I'm a climate guy. So obviously for me, that climate node is the most important thing up there. And so I'm going to work on climate. But in a wicked problem sense, even if you were wonderful, even if you did everything you could about figuring out how to avoid climate action failure, you'd still be unsuccessful because that's so connected with everything else. So, in the trainings that I give for executives, I try to make these points, is focus, and here comes solutions, right? It's a change in mindset. It's a change in how we actually deal with problems is part of solutions, I think. So, focus more on the connections between the nodes rather than the nodes themselves, okay? And you'll need somebody who's a specialist in social stability. You need somebody who's specialist in all of these nodes. But we need general practitioners, if you will, if that makes any sense. We need folks that know what those connections mean, because those connections imply feedbacks. And that's really where the leverage comes. If we can figure out what the amplifying feedbacks are in these complex systems, what the dampening feedbacks are in these complicated systems, these wicked problems, that's where we can make an effect. I've got friends from the Resilience Center here in the room, several of them. We need to prioritize resilience in these systems. Anything that has a feedback loop can be vulnerable, say that 3 times fast, or it could be resilient. This is complex, right? It's a complex image. Don't be afraid of that. One of the things that I enjoy when I work with military executives, if you will, military officers, is the whole complexity thing. They say, yeah, and we can embrace complexity. Let's not try to simplify things all the time. Embrace that complexity, because the world is complex. We're all in this together. Let's lean on each other. We need each other. There's an Ubuntu philosophy about this whole thing. I cannot be my best me without you. We cannot solve these wicked problems without each other. So let's learn to work with and lean on and depend on each other. Be courageous. This does require some courage. So I want to leave you with this. We don't have time for pessimism. Johan told us yesterday that we got to get on with things, right? We can't wait around another 20, 25 years to solve these problems. We need to do something. You tell that to folks, and a lot of time you get the response, or at least I've got the response, well, we don't know how. It's too expensive. It's too complicated. It's going to take a long time. And to that, I would say horsepucky. And that's where this image comes from. Okay? This image was taken over a century ago in Alaska, in 1909, end of April. That's my grandfather, Frank. Frank Noone, everybody? Everybody? Frank? Now, it's cool that it's my grandfather, but that's not the most important or the most relevant thing in this context. And the relevant thing for me, anybody, is to look at Frank and Company's main method of transportation. This is 2 generations ago. That's my grandfather. 2 generations ago, the main method of transportation for Frank and Company was horses and a sledge. Okay? How many of you are wandering around with horses and sledges these days? Okay, not too many of us. So in those 2 generations period, we have already completely transformed our transportation sector. Okay? Frank Noone had never did travel on an airplane, right? We've done that transformation. In that 2 generations period, we've already transformed completely our energy sector. In that 2 generation period, we've already completely transformed our agricultural sector. So the idea that those transformations are too complex or too expensive, nonsense. We've already done it. We need to do it again. We need to do it faster than that 2 generations period. We need to be smarter about it. Okay? That's the challenge. And that's where I'll stop. I'll stop with a picture of a couple of mammals that live close to where I do. Because it's always nice to stop with horse pictures.
Yeah.